Slack meetings. So, I see. So, I don't think I can, I mean, I looked through our Slack meetings. There's a problem, which is that Michael is effectively always correct, and on a good day I try to be correct like 10% of the time. That might be generous. So most of our Slack meetings are long sequences of me saying something and him saying, huh? What? I don't understand. And then eventually he would say, I'm getting sleepy. So Aaron's talk was, I guess you proved the faster the algorithm, the slower the talk, but it was technical. I'll try to be less technical, because one of the things that I'll miss most, perhaps from a selfish perspective, is just Michael had a really strong intellectual curiosity, so what it means is that if you found something beautiful and you got him to think it was beautiful, like that was just really cool. So let me tell you a little about my sort of experience with Michael over the last three or 4 years, and some of the ideas he thought were cool. And then, if hopefully there's time, I'll give you another example of one of these arguments where things were very complicated and he just did it the correct way. So that even maybe seems straightforward in retrospect. But the first time I met Michael was, I think, in Providence, April 2014. I know because I have a G-chat with my girlfriend where I describe an extremely persistent kid from MIT. I'm going to assume it was Michael. And he was working with Richard Peng on this problem of, so it's the following problem. You have a D by N or N by D matrix. So this is, not switch colors. Yeah, okay. So this is a linear operator. So this is just a matrix. And you should think about D as being much smaller than N. So you're mapping some d-dimensional subspace into a n-dimensional, some subspace, some d-dimensional space into a small subspace of some bigger dimensional space. So what you could try to do is you could try to approximate this map by something where the dimension in the image was much smaller. Okay? So what I mean by this is maybe come up with some A prime, from little d into big D dimensions, where now we want big D to be much smaller than n, and we want to preserve some properties of A. And in fact, maybe even better, we just want A prime to be some subset of the rows of A. So just choose a subset of rows of A so that we preserve some properties of the map A. Okay? And maybe the most natural thing you could do is ask that you preserve the norms of all the vectors under this mapping. So ask some kind of condition like this for all x in Rd. Right. So okay, and again, so think about A prime as choosing a subset of the rows in A. So the case p equals 2 is pretty, I mean, classical is not the right word, but pretty well understood at this point. Does anybody who does not consider themselves an expert know how to do it for p equals 2? Like, well, how do you sample A prime? How do you sample the rows?
So if we stay silent, we have to consider ourselves an expert.
Yes, exactly. That was what I was. In fact, you're the person I had in mind. I was going to give you a hard time. So, teacher, you're not an expert.
I'm not an expert. And I think it's used leverage scores.
Yeah. So you do this importance sampling where you sample rows proportional to weights that look something like this. So AI are the rows of A. This represents how important the row is to the span there. So for instance, I mean, one instantiation of this is if if A is coming from a Laplacian, so the AIs correspond to the edges, then this would correspond to sampling according to effective resistances. So that's what happens if you want to preserve the 2 norm. But you can ask about maybe the next most natural thing to think about is what about p equals 1? And so this is what Michael was asking about in 2014, because he and Richard Peng had some notion that Talleyrand might be solving this problem in one of his papers. And in fact, only now on sort of thinking about, talking about some of Michael's work, that I go back and look at what they did there eventually. And it's a really beautiful treatment of something called Lewis weights, which are that if you care about LP norms instead of L2 norms, then there's another notion of leverage score that you should use to sample. Right. So in the case p equals 1, the notion is, well, you want to choose weights that satisfy the following. So let's see. So these are the weights you want to use. And then, oh, sorry, when I say these are the weights, what does it mean? So it's not even, this is a circular definition of the WI, so it's not clear that such things exist. But you can write down an optimization problem for which these WIs are the solution. And they exist for every p, you can do this, for every p greater than or equal to 1. This is the condition you want for p equals 1. And then if you sample with respect to these weights, then actually Talleyrand showed in 1990 that you can match what's known in the Euclidean case. So what Michael and Richard did was, first of all, they understood what's going on there from a CS perspective. So in particular, they managed to do all of this sampling in input sparsity time, very fast. But also, I would take a look at the paper. They did this really nice thing that computer scientists do when they read math papers, which is like to want to think about everything from scratch, which is sort of can be frustrating, but also leads to a lot of really beautiful insights. So yeah, so this paper is really great. Let me just say here, to lead on to the next thing, that what's the major problem in analyzing this? You have this A prime, it's a random matrix, usually a random subset of the rows. But then this condition you have some condition you want to hold for every vector in RD, right? So you can't really take just a naive union bound here over all the, you can't just say, well, for every vector I do well, and I just take a naive union bound. I mean, there's infinitely many vectors. So you end up with looking at, for instance, sort of, so you end up needing more clever union bounds. One of the cases in which, like maybe the most classical area in which that arises is the study of Gaussian processes. And actually that brings me to sort of another conversation I remember with Michael from 2016. We were at Banff, and there's this Banff airporter that you take for 2 hours from the Calgary airport to Banff. And I had just come back from Prague, actually, from Yuri Matuszek's memorial conference. And I was really tired and kind of grumpy, and so I just wanted to sleep and put on my headphones. And then I saw Michael on the shuttle, and I'm like, oh, okay, because he's so I tried to indicate that I was, I put my headphones on. So but then I have to say that, like, Michael really drew me out of my shell. He had just come back from actually this, I think, a chaining workshop that Jelani organized. And so he started asking me about, was that 2016? Yeah. June,
after start.
Right. So this was in July or I think, or August. And so he started asking, so James, I saw on your blog you do this majorizing measures theory, but you don't prove this lemma of Slepian. And I said, yeah, it's you have to do some stuff. And he's like, well, do you know how to prove it? And so, like, the end result is that I'm sure annoyed everyone else on the shuttle for the next 2 hours by trying to reconstruct. Because what I told him was that actually Gromov claims that this was proved by Archimedes. Let me just tell you, So seriously, and Michael really liked this idea, so we spent the next 2 hours trying to reconstruct Archimedes' proof. I mean, the purported proof of Archimedes. So okay, so let me just tell you what Slepian's lemma is in a simple language. So you take n vectors in Rd, and then let's take some other vectors, y1 through yn, and we want the following property, that all the pairwise distances between the xi's are smaller than, or at most, all the pairwise distances between the yi's. So we take some, two families of vectors. All the xi's are correspondingly closer together than the yi's. Then what Slepian's lemma says is that the expected, so now you're going to choose a random direction, and you're going to look at the expected maximum projection of some vector in that direction. So random direction means that this G is an n-dimensional Gaussian, so mean zero identity covariance. And Slepian's lemma says that this is, if all the pairwise distances are smaller, then actually the expected maximum projection over the xi's is smaller than the expected maximum over the yi's. Okay? And the point of the connection here is that here you're looking at a maximum, which is the same kind of thing you're looking at here. And in fact, the way that Talleyrand analyzes this is by using Gaussian processes. But the idea here is that if xi is strictly closer together, is at most it's closer together than the yi's, then the expected maximum is smaller than the expected maximum for the yi's.
Yes, but this seems to be not translation invariant. Like what if you move all the xi's very far from the origin? Maybe there is some assumption that the center is the origin or something like that.
What's wrong? Everything's okay if you translate it.
No, the assumption is translation invariant, but the
No, this is all, I mean, you have expectation 0, so it's expected. What's
well, push all the xi's together very far from the origin, then it seems the maximum would become larger.
I mean, you're going to get. I mean, first of all, you're going to kill. Half the time now, you're going to get a large negative term, for instance, from this thing, and it's going to kill some of the. So, okay. So, what it suffices to do is look at the. So, okay, this is true, but.
No, I guess if you had the same constant, all the xi's, you could decompose it and the expectation.
But just.
Cancel out because of the gradient.
But you just look at you just subtract one vector, just subtract the fixed vector from all the xi's. Look at the expected maximum. That will come out and has expectation 0. So you can translate everything back to the origin. Okay, so here is the so consider the same setup, and now suppose you also have some numbers r1 through rn that are those are some radii. Then here's the fact which Gromov attributes to Archimedes, which is that if you look at the intersection of all the balls around the xi's, look at the volume of that intersection, just a bunch of balls in Euclidean space, take their intersection, take the volume, then the claim is that this should be monotone when the distances when all the pairwise distances are decreasing. Does it make sense? You have a bunch of xi's where the pairwise distances are smaller than the yi's, then the intersection of any family of balls around those centers has larger volume than for the yi's.
That's true for every R1 to Rn.
Yeah. So, and in fact, it's not so hard to show that those two things are equivalent. And then what Gromov says is that this fact must have been known to at least to Archimedes, certainly by the 17th century. It was well established with no references, but it's kind of it's amusing, first of all, because, for instance, even the fact that the intersection of these balls being non-empty implies that the intersection of the balls around the y's is non-empty. This is due to Kirsch-Brown. It's the main step in what is called Kirsch-Brown's extension theorem. So I will just say that with only a little bit of cheating, Michael did manage to figure out the
The other way around.
Yeah. That doesn't make sense.
yeah. Good. People are paying attention. Yeah. Michael did manage to figure this out. And so I'm giving you guys the same challenge. Once I told him that perhaps the key is that you can, given any two such configurations, you can continuously move from one to the other in a way where the Euclidean distances are always decreasing the whole time. So you can start at time 1, or time 0 at the y's, and then move continuously so that at time 1 you're at the x's, and all the pairwise distances are decreasing the whole time. So now you want to prove this along that process. Okay, so now in the last third of the talk, let me tell you how a really nice argument of Michael that actually gets around needing to use Gaussian processes. And I didn't know Jelani was going to be here, so my fingers are crossed that I don't say something silly or offensive. Okay, so this is about these things. Oblivious subspace embeddings. So Michael has a paper, I think in SOTA 2016, analyzing these things in a way which is sort of, at least for me, obviously the right way to do things. But you didn't make any facial expression, Jelani, so I don't know if. Okay.
I mean, it's not going to get the optimal result, but it's.
So in that sense, it's not because it's the log D.
Yeah.
Okay. But it's still the best known result.
It is.
Okay. Yeah. So the idea is that you want to have a random linear map, so a random m by n matrix from Rn to Rm. In this case, you want to think about m as being smaller than n, and you want. So if you think about, for instance, the classical Johnson-Lindenstrauss random projection lemma, then that basically says that you want a random linear map that preserves most one-dimensional subspaces. But here you can think about you want to do some kind of numerical linear algebra. You might want to preserve some higher rank structures. Like if you want to do SVD afterwards, or regression or clustering, some kind of labeling. So the condition you want here is the following: that with high probability you preserve every d-dimensional subspace here. So this pi is against a random mapping, a random linear map. If I don't put a subscript in the norm, it's the 2 norm. Okay, so this is the kind of condition you want. For all subspaces of Rn of dimension d. So there are 3 parameters here. There's d, epsilon, and delta. But does it make sense? So for every subspace of dimension d, you want to preserve all the norms in that subspace with good probability. So if there's some rank d structure, say hidden, like you have some other, you have some other, if there's some rank d structure you have, I mean, this map pi is oblivious to kind of whatever you care about, right? It's some random mapping. It doesn't depend on anything else. But the point is that this map will preserve some, rank d structures with good probability. Now, if you only care about some rank d structure, then it's possible that you can just do something d-dimensional afterwards. Like Luca, this is very similar to the kind of thing we use in the spectral partitioning, for instance, to preserve. Okay. Okay, so if you want to use, if you're willing to take this matrix pi to be dense, then you can just use the classical theory to analyze this. But if you want things to be really fast, it makes sense to take this to be a sparse matrix. And maybe the simplest distribution over sparse matrices that one can think, I have problems with matrix dimensions. I think this is how matrices look. Okay. One of the simplest distributions you can think of is to just put a constant, have the matrix be mostly zeros, but just put a constant number of non-zero entries per column. So like, let's say S at most order of 1. It doesn't, I mean, this is entries per column. And then if there's a non-zero entry, just choose it to be, the correct scaling is to make it, let's say, so if something, most things are 0, if something is non-zero, then you make it uniformly plus minus 1 over the square root of S. Okay? So this gives a very, this is a very sparse matrix, has only linear and n number of non-zero entries. It's much harder to analyze this kind of thing for such matrices because there's not very much randomness. And, sort of like if you're going to be taking union bounds, you want to have lots of randomness. There's not much here. So, so previous analysis of these things, there's a very nice paper of Cohen and Nelson using some fairly technical-looking combinatorial arguments. There's a paper of Morgan. What is this guy? What's this guy's name? Dietster? Dinkster? Dirksen. I knew it was something in that genre of name. Dirksen and Jelani, which is like 85 pages long or something. Is that an underestimate?
Yeah, I mean, it's not just about this.
Sure, no. It does this in a much more general. It does these things in a more general setting. Although, okay, you can ask yourself if this can be done in a more general setting, and you probably know the answer. So that's why you would ask yourself. Okay, so let me just say that. So what did Michael prove here? That the best known bounds in the setting, that this works when. Let's say there's some parameter theta that you get to choose. Maybe you should choose it bigger than 1. It's not so important what all of these things are. But you can choose the embedding dimension m to be roughly d over epsilon squared times some other stuff. And you can do that with sparsity that is something like epsilon log theta. Okay. The only real important thing here is that this is tied up to the. I believe this would be tied up to this log d factor, but I'm not exactly sure. Okay. And previously, the analysis of these things at least lost some additional polylog d's in various places.
James, you want the matrix to be sparse for efficiency considerations?
Yeah, it's much faster to multiply by a sparse matrix. I mean,
but the analysis would be easier for dense random matrices.
Yeah, for dense random matrices, there's enough. I mean, it depends. But if this thing was a random Gaussian matrix, then that's really nice. Every subspace is the same. You just need to consider one subspace. Okay, so what's the? Yeah, so let's see if in 3, I think I get 5 minutes, but okay. So in 5 minutes, I can just tell you Michael's very simple idea. So, okay, so this is the distribution on matrices. The first thing is sort of the straightforward one, that it suffices to bound the following. Okay, so here, this is the operator norm. I'm going to write 2 to 2 norm. This is just the largest eigenvalue of this matrix. So if you can prove that the largest eigenvalue of this matrix is at most epsilon for every u that's an orthonormal basis. Orthonormal. This is it's not hard to check here. If you look at the definition of the spectral norm, it means that these two things map every input vector to be pretty close to, By the way, this is the identity if U is of this form. So we just want to show that for every such U, which specifies an orthonormal basis, that this thing is close in the spectral norm to the identity. And then, okay, so you can just write this down, not this. So I'll write down the thing you care about. This is a random matrix. It's an unbiased estimator. So what happens is, for lack of time, let me just write. What you get is you get some basically diagonal terms. That's just U transpose U. And then you get the off-diagonal terms. So let's sum over R, sum over I not equal to J, sigma Ri, sigma R J, Ui, Uj transpose. Okay, these sigmas are these variables that are mostly 0, sometimes plus or minus 1 over the square root of S. So then, okay, so, all right, well then subtract off. Now what you really want to bound, what you really want to show is almost surely at most epsilon is the spectral norm of this thing. And there's a natural thing to want to do here, which is just define this to be some symmetric matrix ZR. This R here, this is summing over the rows, right? So probably we want to sum 1 to D. Yeah, to define this to be ZR, and then to use matrix concentration bound. That would be like if you were coming in on day 1, you'd say, look, I have a bunch of matrices. I want to use a matrix concentration bound. The problem that you confront is twofold here. One is that I guess the major problem is that, well, these terms are not independent because of the way we selected things, right? I mean, if you tell me that if you tell me this row, obviously it affects the distribution of the other rows because I have exactly S non-zero entries per column. So you can't really use a matrix as a black box, a matrix Chernoff bound. So I could just say that the proof works. Let me say one more thing. I mean, the point is that instead of a matrix Chernoff bound, you can say, well, you basically use a matrix version of a Zuma's inequality, which doesn't require that the summons are independent. It just requires that conditioned on some subset of rows you've seen so far, that you can say something nice about the conditional distribution of the next row. But that also clearly doesn't work because, I mean, if I, for instance, if I tell you the first, like if I tell you the first m-1 rows here, and I don't know, you see, I mean, if you see all of the S non-zero entries already, then there's no variance left in this entry. Or this entry, what's more painful probably is that this entry could be forced to be 1 if you only have S-1 things beforehand. Okay, so you just split the matrix into two. Here it's only confusing because I'm in M from doing things with M instead of D for some reason. But yeah, so Michael just says, okay, just split it into 2 pieces, and then just bound this quantity for each piece separately. If you've only revealed half the rows, then this is not really an issue. Because I mean, you have S is some small number, and so if you've only revealed half the rows, then you can't. I mean, you can think about it. It's not particularly difficult to show that the sort of the conditional distribution still has nice concentration properties. Okay, but that's the whole argument. There's one other step here, but it's not involving decoupling, but it's not particularly But that's amazing, right? That's the whole, okay, so you say you want to use a Zuma, so then you say, well, you can't, so just split it into 2 pieces. Now you have to take a unebound over twice as many things, and then you finish the proof.
Is this the decoupling technique?
The decouple, okay, there's some decoupling here, because if you look at this term, it looks almost like it should be a square, except it's not a square because you have I not equal to j. But the decoupling argument says you take this sum, you write it as, you can write this sum as an expectation over sums that look like this. Let me write it here. Then we're Ri. What was the variable? Oh, okay, right. Ui. So that sum is actually the expectation of this sum over all random partitions of the coordinates into two sets. And therefore, if you care about some convex functional of this sum, then you upper bound it by Jensen by a convex functional of these things. Now you're left to analyze, say, for every t, something of this form. But now notice that these two parts are independent because they're on disjoint sets of coordinates. So the randomness here is independent. So that's the decoupling step. So there's like decoupling, and then you have to deal with sort of the harder issue. That's this the fact that you might not have very much randomness left once you condition. So he just splits the matrix into two pieces and then analyzes each one separately. They're not independent, but it doesn't matter. You just increase the union bound by a factor of 2. I like this proof because it's the kind where, like, okay, now I know how to prove it. Like now you can be in on a shuttle ride in Banff and somebody asks how to prove that sparse random matrices are good subspace embeddings.
So James, the extra log D in the bound comes from the fact that when you do matrix Chernoff type things, there is an extra n in the probability, so you need an extra log n to give it.
Yes, in fact, there was, if you remember the first part of the talk, there was a log D. That's the same log D. All those log Ds possibly can be removed. And we know situations where they can be removed. Batson, Spielman, Srivastava is one such situation. But they are all from taking a union bound. They're all from.
Log D entries per column, or is it really a constant number of entries per column?
It's what I wrote. It's what I wrote here. So so it's true that if you want to get really this dependence on D, then you have log D entries per column. Okay. And just to say one more thing about Michael, let me say that all of these, people have been throwing sort of these one sentences, and then Aaron mentioned like an interactive argument to decipher what they mean. So one of the minor unfortunate things about Michael passing away is that when we were trying to write our stock paper with Seb and Yintad and Oleg, the day before the deadline, we spent basically the entire day trying to figure out what one of those sentences means. And we managed to do it, but it wasn't so easy. All right, that's it.
Thanks, James. I think you were generous with saying that it was just one day.
For that one sentence.
Is there more questions or comments?
Does this have something to do with Hansen Wright?
You want a yes or no answer? Because I can't. No. But also, yes. I mean, Hansen, right? You want to bound like chaos, like degree 2 polynomials in the random variables. But this is all degree 1. So like, I mean, you mean here because you have this kind of thing. This is not, but that's not. Oh, they do. I mean, decoupling is something that goes on all the time. So also in Hansen, right? But this is not really a quadratic. I mean, you don't need to analyze it like a quadratic.
I don't understand what's happening personally, but I just saw the splitting up in their proof.
Decoupling happens all over the place. So there is actually a really good paper of does anybody know who's on the paper with Ryan? They have a paper that has a nice survey of decoupling methods. Okay, Ryan O'Donnell and a student who I don't remember.